Okay, welcome to part 2 of simple linear regression. What we did last time is we built that basic regression model and how regression works, the straightforward intuition that relates to that y equals mx plus b format. Of course, now b is beta 0, m is beta 1, x is still x, y is still y. We also introduced the idea of the residual, that little bit of leftover, that part that we cannot explain, that difference between what we observe and what we predict. Here's what we were talking about last time. We can see the residual here. Here is, by the way, our Rainbow Professor data with our quality and our difficulty ratings. And then we have our predicted values, our predicted qualities based on our regression that we have down here. And then the residual left over, the difference between what we predicted and what we actually observed, what we think the quality is and what we actually observe. Visually, we can see this with a scatter plot. So let me show you the scatter plot version. In order to do the scatter plot, though, when you make scatter plots in Excel, keep in mind that the variable on the left is going to be your x value, and the variable on the right is going to be your y value. So we have to switch these. And this is something you should learn how to do when you're working with Excel, and especially if you're working with regressions, especially, as we will discuss later, multivariable regressions. You have to get everything next to each other. You have to put them in the right order sometimes. And that's going to require cutting. So I'm going to right-click, I'm going to cut. And then whatever column you right-click to paste, Excel will put that into the left. So I'm going to right-click D and insert cut cells. And now difficulty is on the left, quality is on the right. So let's highlight. Careful not to press the actual link. And we're going to insert scatter plot. So here we have difficulty on this axis, predicting quality on this axis. Now, if you don't want to go through all the steps of regression that we showed you how to do, there is a very quick and dirty way to do this. I don't recommend doing it this way because you won't get any feedback on statistical significance or any of the other things we care about, but it is super fast. If you right-click the dots and you go to the Add Trend Line option, this area will come up on the side, but you see here is our trend line. Here I can make it more visible. Let's, for example, I'll make it blue but black. There we go. Ooh, and let's give it a solid line. This is our line. This is our estimated line. We can even see display equation on chart. It will print it in the form of y equals mx plus b. And we can see there's the same result. So here is the b, or the beta 0, the y-intercept, 6.21, 6.21. And then here is what's multiplied by our independent variable, negative 0.862, negative 0.862. So it's exactly the same line. Again, it doesn't tell us statistical significance, so I don't recommend doing this just to do a sort of general analysis. Getting statistical significance is really, really important. But we do see this basic idea of this is what, so for someone who has, say, around a, whatever that is, 3.8 difficulty, we would expect them to have a quality of about 3. That kind of thing. That's our fitted line. But what's neat about this, and this is what we also discussed last time, is we can now see who has the highest residuals. In fact, this person might be the person who has the best residual, right? It is 3.8. A 3.8 difficulty and a 4.2 quality. 3.8 difficulty, 4.2 quality. This person, as we discussed last time, is a very good professor. At least that's what our analysis suggests. Again, it's tricky to do this kind of analysis with this data because of the bounds issue. You know, like you can't have a rating higher than 5, you can't have a rating lower than 1, and so forth. But still, this is something worth thinking about, something worth considering. We would expect this person to have a rating, you know, right about here in the in like the high 2s and maybe a 3, but they actually have one all the way up here in the 4s. Similarly, this professor over here, we would expect them, given how easy they are, to have a rating that's in the 4s as well, mid 4s, right, based on this predicted line. But they are actually all the way down here, this really negative residual. They're in the 2s. Oh, I can just mouse over it. You know, they're like a 2.4 for their quality. So suggesting maybe this person isn't that good, or say the same thing here. This is a different version of the same idea, but just from the notes, it's a little bit more visible. Right? We would expect to be here, but we're actually all the way up there. Based on this setup of difficulty causing quality, we would expect this person to be all the way up here, but they are actually down here. They're actually in this much lower area. Some negative residual suggests that maybe they're not as good as we would expect them to be. They're not as good as maybe they seem to be, because, you know, 3.7? That seems all right. That's pretty good. You know, not actually. Oh, this is such a huge, look at how big that residual is. It's a massively negative residual. Oh my goodness, that's like, it's like over a 1.5. Wow. Okay, there are negative 1.8, negative 1.7. Some people have really big residuals, negative residuals. Some people have really high ones too. Okay. Now, it's important to remember that when we were running these regressions, something I mentioned was we are telling a causal story of X causing Y. As in, if you change X, that causes Y to change. But if you change Y, when you can't directly change Y in this circumstance. If you change X, Y changes, but not the other way around. That's based on certain assumptions of what we're working with. It's based on that's based on the logical story we want to tell. But you could argue that story is wrong. So we're telling the story of, if you make the class easy, people will like the professor and they will rate the professor higher. But what if it's the other way? What if instead, what if it's quality causes difficulty? What if we're suffering from reverse causation? What if we're making a mistake? What if instead of difficulty causing quality, what if it's quality causing difficulty? Now, we can't just flip them for no reason. We need some sort of logical story that we could tell that would justify why quality would cause difficulty. So take a moment and try to think of some logical reason as to why that would be. Why does it make sense? Why would it make sense that quality causes difficulty? So a previous story was, if you make the class easy, people like the professor and they'll give them high quality. But what if the story instead is that if you're very good at teaching, the class seems easy, the material seems easy, and so as a result, people think the professor is not very hard. But really, the professor is so good that the material just makes the material so intuitive that it just seems like it's easy. It's possible you might think that that's a silly theory, you might think that's a reasonable theory, but it's not a completely nonsensical theory. It's not a theory that literally makes no sense. It's not a theory that's saying, like, my income now caused my education in the past, right? That's clearly impossible. It's not possible for what's happening now to affect things in the past. But this is a possible thing. So we have if it's difficulty causing quality, then we have quality. Now, if we're going to instead say difficulty is caused by quality, that quality causes difficulty, if we're going to flip it around, it seems like it's just a matter of algebra. It seems like it's just a matter of algebra to flip these two around, to go from this one to this one. And so it's tempting to be like, well, I don't need to rerun the regression. I can just isolate D and do a little math. Subtract 6.21 from both sides, and then divide each side by negative 0.86, and then be done. You can't do that. Don't do that. That won't work. Because you have to think about why the regression is what it is. Remember what we talked about last time. This line that we draw is meant to minimize the residual sum of squares. The squared residual and then summed across all observations. Recall a residual is a vertical distance between what we observe and what we estimate. So if you decide to flip it, to change your x and y variables, you fundamentally change what that vertical distance is, right? It's no longer about this, it's about this. And it's not clear at all that this line, right, would then result in would then be the result, like this sum squared difference would suddenly be the smallest way. In fact, it's not. So you can't switch your causation by just doing some algebra. You have to rerun the regression, right? If I think it's actually quality causing difficulty, then I have to rerun the regression. To illustrate this basic idea just as quickly as we can, let's copy, and then let's insert copied cells, and then I will highlight this whole thing. And I will make another scatter plot. And now notice that it's difficulty here, right? So these are actually mirror images. What you see, all those clumped up right there, they're now over there. So let's add the trend line. Just to harmonize it, let's make it a solid line that's black. No dash type, just a solid line. And more importantly for our case, display equation. Now, before I hit the display equation, think about what this would be if we just isolated D. Now, that means the value here that will be multiplied by Q will be 1 over this. It would be Q minus 6.21 equals negative 0.86 D, and then we divide, and so that would be 1 over. So the coefficient of 1 over 0.86, that's clearly going to be greater than 1. But when we rerun the regression, it's not greater than 1 at all. D equals 5.38 plus a negative 0.67 Q. A completely different line. I can further show you this is a completely different line. So just as before, here's quality causing difficulty. Right, this is what we just did. Now note the professor with a quality of 2.4 and a difficulty of 4.4. Quality of 2.4 and a difficulty of 4.4. He's way above the regression line. If it was just a simple matter of mathematics, of flipping the x and y axis, professor would also be far away from the regression line, but they're not. Here they're way above it. Here they're right on it. On the right is quality causing difficulty, and they're way above the line. On the left is difficulty causing quality, and they are directly on the line. It's a completely different line. You have to rerun the regression. You have to rerun the regression because linear regressions minimized what is summed and squared vertical distances. The vertical distances. In order for linear regression to work in that pure nice way that we saw and the nice we've been doing it, we have to make certain assumptions. This is not all the assumptions you have to make, but we're going to cover 4 big ones in order to help understand the limits of linear regression. It's a very powerful tool. I ran into someone today that talks about how they use linear regression. And it was yesterday. The days are kind of blending together. Yeah. Regression is a very powerful tool, but we should be aware of its limits. And so one way to understand its limits is understand the underlying assumptions that we make when we make these. Now, for your paper, you're kind of just going to assume all these assumptions, but you should be aware of the practical realities of these assumptions, the limits, the boundaries of this tool. Assumptions of linear regression. 1, the relationship is linear. I know it sounds stupid, but here is a relationship where the values are decreasing, the values are increasing and then decreasing. This is temperature and revenue for some company or something. It has this inverted U shape. And if you try to draw a line, it will give you a line. It might even give you a statistically significant line. But it's clearly not a good fit. It's clearly not really a good predictor about what's going on. Because you can't obviously put a curve on a straight line. Right? If the pattern of the data is curved, but the line that you draw is inherently straight, you're not going to get what's going on. Now, granted, it's a relatively easy thing to relax this assumption. In fact, Excel even has some of that stuff built in. Excel has some of that stuff built in here. So when we click on it, we can make it an exponential, right? We give it a little bit of curve, or logarithmic, polynomial, right? This is kind of a linear relationship, so I'm not seeing too much. Don't press that button. This is kind of a linear relationship, so I'm not seeing too much, but we can add. But that polynomial will give us a nice curve, and then we can add more. And you see now we're just cubing and squaring, power 4 or 5, 6. It's a relatively easy thing to throw in. But for our purposes, linear is fine. Here's another example. Again, it has like that clear curve to it, but you're just trying to map on. In other words, it should make sense that the slope is constant. 2, if you were to plot the residuals, you would get a normal distribution. If you plot the residuals, it would get something like, looks like a normal distribution. I'm going to actually test it to see if this does, but we have all the residuals, right? So here's the residuals. Highlight all of them. I'm sure that zero's there, so it's left over something. Oh, that's when I summed it. Recall, we talked about how if you sum everything up and you add them all together, all the residuals together, you get 0. So let's see if we take that. And just to get an idea, I'm not going to go through the whole rigmarole. I just want to do a histogram, a basic histogram. And it looks like a normal distribution. Oh, that worked out well. We have, you know, it's a little bit left skewed here, but it's not like all the residuals are super, you know, all the residuals are either super big and super small. It's not like it's a U-shaped or anything. It's a nice kind of most of the residuals are near the center, and then it tapers off. So not perfect, but that's pretty good. This works out pretty well. Three, the residuals are independent from one another. So in order to understand this and what it really means and what it really implies in practice, I'm going to take a side trip into time series. So recall that regression analysis has an X variable and a Y variable in this basic setup. Well, you could make time as one of your variables. You can, for example, have year. And then income. But you can make a time series about it. There's no problem. And this might be 2020 and 2021 and 2022 and 2023. And then you might have some plots of your income. And then you can make a regression and then project your income into the future, right, based on past performance. There's potential problems and pitfalls with that, something we'll talk about later, but generally speaking, you can certainly take a time series and apply it to a regression and do a projection into the future. That's a perfectly fine, acceptable thing to do. That's what companies do all the time, various versions of it. And this does a lot of complexity with seasonality and all that stuff. But more or less, that's something you can do. The reason why I bring this up, though, is because the reason why I bring it up is this doesn't always hold. It's not typically a big deal for the panel data that we're talking about, but it does come up a lot in time series. One way to think about this assumption is it's essentially saying you can't see a pattern of the residuals. And the reason why that matters here is because which professor we have in order is totally arbitrary, which is the first professor or second professor or third professor, totally arbitrary, right? We base it on their names, or their first names, their last name, or how long they've been to school, how many ratings they have, it doesn't matter. But there is a logical order for time. There is a logical order for time. The earliest observations are at the beginning of the data, 1, 2, 3. The later observations are n-1 or n-2 as the last observations. And so because there's a specified order that makes logical sense, that has this impact on the world, then you can very easily get a pattern in the data. A pattern, I should say, with the residuals. You can very easily get a pattern with the residuals. And we call this autocorrelation. So one of the assumptions is we have no autocorrelation. So here's such an example of autocorrelation. But you see there's a clear pattern of the data. Right? The data form a normal, the residuals form a normal distribution, let's just say, but the residuals have this very clear pattern. You can predict one residual by looking at the previous residuals. It looks like they're totally random numbers. That's what the top part is. But the residuals show a sign function. That violates one of our assumptions of regression analysis. Right? the residuals have to be random. They have to be independent from another. Last major assumption, and again, there are other assumptions and complexities and so forth we can apply to linear regression, but these are the big four we're talking about. And the last one, this is one you're going to have to take practice to pronounce: homoscedasticity. 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 Homoscedasticity is a description about what the data look like. It essentially says that the spread of the data away from the best fit line, from this predicted line, is constant. Constant dispersion of observations from predicted line. To illustrate homoscedasticity, one way to illustrate it is to illustrate heteroscedasticity, when that variance is not, that dispersion, I should say, is not constant. One way to illustrate homoscedasticity is to turn to heteroscedasticity, when the dispersion is not constant. For example, here is a plot of homeownership versus income. It's a little hard to read, but you get the idea. I think these are individual points are probably neighborhoods. So a neighborhood where income is very, very low, no one can really afford a house. So ownership rates are very, very low. But as neighborhoods get wealthier and wealthier, as the average income goes up, then ownership rates can go up, but they can also stay low. They can go up, obviously, because if you are wealthy, if you have more money, I should say, then you're more likely to be able to own a home. But they could also just stay low because maybe the cost of housing in that area is really high. But it's never so low as to make home ownership feasible at very low incomes. So in other words, the data is really tight there at the bottom. It's really close to that best fit line. But then as you get to higher levels of income, the data spreads out. The dispersion from the best fit line is not constant. Just as a side note too, homoscedasticity, I'm spelling it with a C, sometimes it's spelled with a K right there. So just in case you see it differently, it's the same word. I think I kind of prefer it with a K, but I think I always do it with a C because a lot of textbooks use it with C. I think K looks cooler, especially since I don't like the letter C, because sometimes it's, has a hard sound like cat. Sometimes it has a soft sound like an S, like a circus. So sometimes it's pronounced like a K, and sometimes it's pronounced like an S. And what are you doing? So, homoscedasticity would kind of like this. So it's really nice, consistent variance. While heteroscedasticity, the variance is not constant. And there's a lot of ways, but you can do it in this one. I have to draw it like this, where it got wide and then it gets narrower. And in this example, it was narrower and then it got wider. Maybe it's wide and then it gets narrow and then it gets wide again. The point is, it's not constant. That dispersion is not constant. The simplest way really to find heteroscedasticity at our level, there's more sophisticated tools to find it. But the simplest way is to just plot our regression, shows the best fitted line, and then kind of eyeball it. Again, I'm not asking you to do that for your paper. We're going to assume all of these four things matter. All these four things are happening. We're going to just assume that the relationship is linear. For your paper, we're going to assume that the residuals follow a normal distribution. We're going to assume that there's no autocorrelation. We're going to assume that there's homoscedasticity, right? Just to make things simple. But in case you're curious, that looks pretty consistent to me. It's not super great, but it's pretty consistent. It gets a little wild over here. But those are just a few of the observations, right? That's only like about maybe 5 or 6 observations. Most of the time, right, we have like over 200, and most of the time it's pretty consistent. And of course, where'd my other one go? There it is. This one also looks good, even better actually. Again, I have to check both because this is a fundamentally different line. And this is also pretty consistent. Right, again, a couple of weird ones, but pretty consistent. Right, just by eyeballing it. So, what does homoscedasticity mean in practice? Like, if you don't have it, if you just have heteroscedasticity, what would that mean for your regression? And just to give you an idea of the role of these assumptions. And it turns out, like on the scale of things that really matter, the homoscedasticity can matter. It usually doesn't, but it can matter. If you have a heteroscedasticity, it will slightly bias your error term, which will, in turn, slightly bias your t-values, which will, in turn, slightly bias your p-values. In other words, that bias can go either direction. It might be slightly higher or slightly lower than it should be. So in practice, if you're doing a more sophisticated analysis, not within the bounds of this class, and you're concerned that maybe you have heteroscedasticity, but you look at your statistical significance and it's all the way up there. It's significant at 99.99999%. Because this is a slight bias that typically results, it's probably still statistically significant. Right? Even if you were to correct the heteroscedasticity, it would probably still be statistically significant. If on the other hand you're barely statistically significant, if you're like, your alpha is like 0.045 or 0.046, then you might be committing type 1 error. You might not have statistical significance when it kind of looks like you do, because you have a bias error term. So that's it. That's the essence of the really basic linear regression analysis. We have these 4 basic assumptions. Again, like there are other things that go into it. Like I said, this data that we're using here with Raymond professor data is really flawed because of these like constraints on how you can rate people. So you don't want to read too much into it. Like, I'm not suggesting that our administration here at the college starts like using this to evaluate professors in a large part, but at the same time, it's just a very nice intuitive data set to work with. So that's why I like working with it. But these assumptions that I put up earlier, those are not all the assumptions. Those are just the 4 big ones we're working with today. So you can get an idea in the semester of like the constraints. There are indeed constraints in linear regression. It's super powerful, but there are constraints. The really cool thing though about linear regression, it's not just limited to just you put only one thing in, depends on the other thing. You can have a system where lots of things depend on it. Like if we're trying to predict quality, we say difficulty matters. What else might matter for quality? What other things might matter? And so in other words, you can add additional variables. And that's what we call multivariate regression, when you have multiple things predicting one common thing. And that's what we're going to be talking about.